I haven't had a chance to look at what you did, but when you see, oops, what did it say, 200? So this is function notation, and this is, it doesn't take much space to write this down, but it's just loaded with meaning, just packed with meaning, right? With what I've written on the board alone, there's not enough information to extract that meaning. So it's written on the paper, but I just don't want to write it down out of laziness. But there's a sentence before and after that explains what the inputs represent and what the outputs represent. And so bearing that in mind, that 100 actually has units. And interpreting it is a lot easier if you know what the units are, right? You know, is that 100 dogs? Is that 100, ounces? Is that what?
100 food processors.
Yeah. So it says clearly that X, or the input, is the number of food processors. So that's 100 food processors. And that 200 also has units. And hopefully it was clear from the statement of that sentence that this is a cost function, meaning that it's a formula for the cost. And so the answers that come out, this 200 has units as well, although I didn't write the units, but it's in dollars. Now trying to interpret this is going to be next to impossible if you don't know what the units are. But once you have the units are, I'd say you're 80% of the way done. Now you just got to be able to compose an English sentence, right? And so something like, it costs $200 to manufacture 100 food processors. I won't mark you down if you misspell things, because I might misspell things too. But yeah, something like that would be enough for full credit. Okay. And the next one is kind of curious. I give you another function, but this time I didn't really give you I didn't give you a formula for the last one either. But I'm giving you the function in the form of a graph, right? And so this is a graph for f as a function of m. And what you see is a line that's going something like this, not necessarily drawn to scale. But if you read the sentence, the key phrase in that sentence that you want to zero in on is it says, in order to produce 20 food processors, right, how many kilograms of raw materials are needed? So you'll notice that there's if you're looking at the graph, you can see that there's a 20 right here and a 20 right there. If you're not paying attention to the units, if you're not paying attention to the context, it's not going to be clear which 20 is the one you're interested in. But since this is, I did specify by saying we're going to produce 20 food processors, you got to think which one represents food processors, F or M? Yeah, F represents the number of food processors. And so what I was expecting you to do is to identify this 20 and then look for a point on the graph that has a F coordinate. I guess I'd ordinarily say Y coordinate, but F coordinate in this case, of 20. And it would be about right here. And then to answer the question, you're going to see what value of M corresponds to that. And if you look directly down, by my estimation, it looks like it's somewhere between this mark and this mark, which, again, it's not drawn to scale, but it should have been clearer on the test, that it's somewhere in between, what, 50 and 55? So I would accept pretty much any number between 50 and 55 for full credit, okay? It's kind of subjective in how good you are at drawing straight lines, right? So yeah, that's how I'll be grading these. I guess we'll probably take a break in an hour and I'll grade them at that time and get them back to you. But that's what's going on the quiz. And so I just wanted to make sure that you're able to kind of be able to understand the function notation like we talked about before, but also too, how to work with a function when it's given to you in the form of a graph. We won't always give you a formula. Sometimes it'll just be the graph. Okay? Any questions about that? Fair enough. I have some loose ends for section 1.1, namely the book, they call it the Toolkit Functions, is that right? Okay, Toolkit Functions. I always forget. This is not an official term, by the way. It's just something specific to this particular author. Okay? So if you go into another math class, the teacher might not know what you're talking about. Okay? Now, this is going to be a list of 9 functions that I would like you to be able to master in time for our first exam, which is actually next week. All right? You just got to know all the ins and outs and all of the subtleties of the shapes of each of these 9 graphs. And for example, this is an equation, right? Y equals X. This is probably the simplest and the most basic of the 9 toolbox functions. And it's called the identity function. And what I want you to know offhand is what graph you would associate with the identity function is. Some of you might know already. But what I'm about to do is I'm going to draw a curve that represents the set of solutions. Okay? What would be an example of a solution to this equation?
1, 1.
Yeah. 2, what's that?
2, 2.
Yeah. Yeah, so a solution would have to involve 2 numbers, right? Because this is an equation involving x and y. So a solution would be, since 1 equals 1, then 1 comma 1 is a solution. Since 2 equals 2, 2 comma 2 is also a solution. That's 2 points that are on the graph, right? Can you think of any more?
3, 3, 4, 4.
Nice. Okay, we get the idea. Can you think of any with fractions?
1/2.
1/2, 1/2.
How about negative numbers?
Negative 1, negative 1.
Yeah, to really get a good idea what the graph looks like, you want to get a good sampling of not just positive numbers, but negative numbers too, fractions and that sort of thing. Once you got a pretty good sampling, you start to get a pretty decent picture of what's going on. And so, you get this. If we were to just do this for the rest of the night, after picking 100 more points, the dots would start to fill in the space, right? This is a function. How can you tell it's a function?
Vertical line.
Right. If you were to imagine a vertical line just scanning across, it never touches the graph more than once. I also want to add in, we're going to go ahead and start jumping into section 1.2 simultaneously. In section 1.2, we're going to start talking about domain and range. If you haven't heard these words before, the domain, the words I was using before was inputs and outputs, right? In reference to functions. The domain is just the set of all the inputs. range is a set of all the outputs. So the moment you said that 1, 1 is a solution, a point on the graph, then you just told me something about the domain and the range. Since 1 is an input, that means that 1 is in the domain. Coincidentally, since 1 is also an output, that means that 1 is also in the range. Make sense? So if you can see a point on the graph, okay? I know this might seem kind of like overkill, but when we start looking at the other toolkit functions, we're going to repeat this discussion, and it might be a little less obvious what the domain and range are. But in short, if you can locate any particular point on the graph, then look down and you'll find a point that's in the domain. Look left and you'll find a point that's in the range. Fair enough? So we also said 2, 2. So 2 is in the domain, 2 is in the range. 3, 3. So 3 is in the domain, 3 is in the range. 1/2, 1/2. So 1/2 is in the domain, 1/2 is in the range. -1, -1. So -1 is in the domain, and -1 is in the range. So therefore, the domain is what?
Negative infinity to infinity.
Yeah. There's actually lots of different ways of saying the same thing. Another way of saying the same thing is just all real numbers. But also in section 2.2, you're going to need to get some practice with interval notation, right? If I had to guess, I would suppose that some of you have worked with interval notation before, some of you have not, okay? This is how with interval notation, write it like that. That's what you said, right?
Mm-hmm.
Yeah, so I can tell you've been exposed to interval notation before. So that's going to help you in this class. But don't worry, even if you haven't learned it before, well, I'll tell you everything you need to know, okay? Now, you have to be very careful with interval notation because it's easily confused with ordered pairs. Much like ordered pairs, which has parentheses and a comma in between two numbers, the interval notation has a comma in between two parentheses, right? Although these don't have to be numbers. In this case, it's infinity, right? But when I write this, though, I just mean all real numbers. And likewise, the range would be what?
The same.
The same. And for now, that's everything you need to know about the identity function. I'll give you a study tip. Everything that I've written on the board are not facts to memorize, although you could, and I won't hold it against you if you do. At the very least, you just need to memorize that this word goes with this equation. And if you understand that much, I think you could just kind of like, just by picking numbers, you can remind yourself of what the graph looks like. And once you know what the graph looks like, you should be able to identify the domain and the range just looking at the graph. And I'll tell you what, a week from today, there's a good chance I might give you a function that's not any of the 9 toolkit functions. I'll just give you the graph on the test. and ask what's the domain and the range. And just looking at the picture, I would expect you to just be able to identify it. So we'll get some more practice with that now. That's the first of the 9. So what's the next one? Yeah, I don't even have it handy. What is it?
X squared.
X squared, okay.
Labyrinth.
Okay, they call this what do they call this? The quadratic function? And in this particular case, I'd say if you're going to be a minimalist, right? If you're going to be a minimalist, that's the minimum you got to memorize. Okay? And so, if, although for the sake of speed, it might take it might take some time period to pick numbers that are on the graph and start connecting the dots. So for the sake of speed, you might want to memorize what the shape of the graph looks like as well, right? But if ever you forget, how would you reinvent the graph? You'd ask yourself, what is a solution to that equation? In other words, give me 2 numbers, an x and a y, that satisfies that equation, such as
9?
right? 3 and 9.
Yes.
3 squared is 9. Therefore, if x equals 3, then y equals 9. So 3, 9 is a point on the graph. So if this is 3, and this is 9, and that's one of many points on the graph. To get a really decent picture, I'd urge you to pick several positive numbers, several negative numbers, and maybe some fractions to see if anything different happens with fractions, right? Can you think of another point that's on the graph?
0, 0.
0, 0. As a rule of thumb, I think it's a good idea to kind of like start simple, work your way up from there. 0, 0 is a great place to begin, right? What's the third point that's on the graph?
4?
2 and 4.
2 and 4. 2 and 4, yeah. And where is 4? Is maybe about right there, I guess.
And negative 2 and 4.
Oh, I like it, a negative one.
I guess it would be negative 3 too.
Mm-hmm. In a way, the quadratic one is kind of nice in that when you find a point over here, you get some other points for free. See that? At this point, we can see there's clearly not a line. 1 and 1 is also on here. Negative 1 and 1 is on here. Start picking fractions like 1/2. If x equals 1/2, what's y?
1/4.
1/4. 1/2 times 1/2 is 1/4. For that same reason, negative 1/2 times negative 1/2 will be positive. Yeah, so I guess in the interest of just speed, you won't have all the time in the world to do the next exam. It might be nice to just simply know off head that a quadratic function typically has this sort of like U shape or a cup shape, right? Also known as the shape itself is called a parabola. When we get into chapter 3, maybe a month from now, we'll be returning back to this and spending a lot of time on it. Okay. Tell me about the domain and the range.
is all real numbers and range is 0 to infinity.
Right, yeah. So that's going to be a, I think it's going to jump out at you, for somebody it's going to jump out at you right away. For those of you, it's going to take a little practice before it becomes something you just look at the graph and just know. For most of us, it takes practice. But I'm going to just kind of warm us up to that. The moment you said that 3, 9 is a point on the graph, I immediately knew that what number is in the domain. 3, right. And 9 is in the range. So if you look down, you'll see something that's in the domain. If you look left, you'll see something that's in the range. Likewise, the moment you said that -2, 4 is a point on the graph, we immediately knew that -2 was in the domain and 4 was in the range. I put these arrows to indicate that the graph continues on. I just got tired of plotting numbers. And so to say that the domain is all real numbers is you're speculating that if I was to continue drawing this graph, then the graph would continuously get wider and wider and wider. And if you go far enough, you'll eventually pick up any real number. That's what you're saying when you say that the domain is all real numbers. But you said something different for the range, right?
That was 0 to infinity.
0 to infinity. And if that question is asked on the exam next week, if you say 0 to infinity, that's a little bit vague, right? It's a little bit vague because, for example, okay, if you're taking notes, don't write it down yet. I'm going to erase this in a second. Okay? This would actually be incorrect. This would actually be incorrect. You see this parenthesis right here is saying that everything between 0 and infinity is in that range. Not including 0, not including infinity. Right? Now it makes sense to have a round parenthesis next to infinity because infinity is not actually a number. But what you'll see is that sometimes I'm going to put a parenthesis next to the 0.
Or a bracket.
Or a bracket.
Okay.
Or a bracket. The parenthesis means that 0 is not in the range. The bracket means that 0 is in the range. So which is it? Is 0 in the range or not?
It is. So
0 to 0.
So because 0 is in the range, to get full credit on a question like this, I'm going to be really sensitive to these teeny little subtleties in this class, right? So the range in this case is from everything from 0 to infinity, but you know, what's difficult for me to say in words, I can make more precise when I'm writing it by putting a square bracket. What's the next one? Like 1 over x or x cubed or something like that.
yeah, x cubed.
Cubic function. All right. If ever you forget what I'm about to draw, just pick numbers and plug them in. Right? 1 cubed is,
1.
so that's the point on the graph. I should take my own advice and start simple and work my way up. What's even easier than 1?
0, 0.
0 cubed is 0.
-1, -1.
-1 cubed. You see why that's -1?
3,
What about 3?
9.
Ah, yeah. Well, let me think. Not 9,
Oh no.
right? 3 squared is 9, but 3 cubed.
27.
Okay, I don't want to write on the wall, but
2?
2 cubed is?
8?
Okay. This is 1, and this is 2. This is 1. Okay, it's not really drawing a scale, but let's just say that's 8. Likewise, negative 2 cubed.
Negative 8.
Negative.
What's 1/2 cubed?
1 and 1/2? No.
8.
You're thinking of 1/2 times 3.
You said, can you repeat the question again?
What is 1/2?
One is 8.
Yeah,
Oh, okay.
that's 1/2 times 1/2 times 1/2. When you're multiplying fractions, the simple thing is just 1 times 1 times 1. 2 times 2 times 2. Okay. So it's pretty close to the x-axis. And negative 1/2 cubed?
Negative 1.
Yeah. So I'm pretty sure that if I was to, if we use the next hour just plotting points and stuff like that, the spaces in between the dots will start to fill themselves in. And it'll start to resemble a shape like that. What's the domain of the range now?
All real numbers.
What about the range?
Same deal.
Thanks. So it looks like the cubic function and the identity function seem to have a lot in common, at least insofar as the domain and the range. Although they're clearly not the same exact function, they have different shapes. What comes after the cubic function?
Reciprocal.
I think if I was to start simple and work my way up, I'd probably begin with 0 for x.
Asymptote.
You can't divide by 0. So I guess we'll have to move on from there. What's the next easiest thing to plug in besides 0? 1. And 1 divided by 1? It's interesting that all 4 of these has 1, 1 on the graph. What's another point on the graph?
Two 1/2.
Which one? 1/2, is that the x or the y?
Well, no, 2 1/2.
Oh, 2. 2 is right here. And 1/2 is between 0 and 1. So something like that.
3 1/3?
Mm-hmm. This is a case where, in order to get a really complete picture, I would urge you to use some fractions too. What is 1 divided by 1/2?
2.
Yeah. Something you, this is one of those things I'd expect you to know coming into the class, is that when you divide by a fraction, it's kind of like multiplying by the reciprocal. You flip it. So division by 1/2 is the same thing as multiplication by 2. 1 divided by 1/2 is 2. Therefore, 1/2 comma 2 is also a point on the graph.
1/3 and 3.
1/3 and 3, right? How about some negatives? What if we pick some negative numbers? How does that change things?
The curve starts off to the left.
Yeah. It's kind of like the same thing,
Just to
but remember a positive divided by a negative is
negative.
negative. So it's going to kind of flip. I would say it's kind of like a double flip. Flips over to this side because of the negative x's, but also flips down because of the negative y's. So for example, if x equals -1, y equals also equals -1. If x equals -2, then y equals. Likewise, if x equals -1/2, y equals. Long story short, this is what I'm referring to when I speak of the reciprocal function. So they're toolkit functions because you want to keep them in your back pocket, ready to go at any time. This one's important enough that it actually has a name as well. Polar hyperbola. Just for fun, you can impress your friends. How about tell me about the domain and the range of this function.
Everything with 0.
Yeah. We couldn't plug 0 in, right? That was the first one I tried. And we had to abandon that idea because we can't divide by 0. Is there, and you're saying that but everything else is in the domain.
So we use parentheses, right? For 0.
Yeah, I haven't told you yet, right? We're going to do everything from, and this is a case where it's actually easier just to say it with an English sentence, everything but 0. And on the tests, if you say that, I'll give you full credit. However, if I specify, and sometimes I will, if I specify that I want the answer in interval notation, then you'll get partial credit for that, but full credit if you give me the answer in interval notation. If I want to say everything but 0, I would say that's everything from -infinity up to, but not including 0, along with, this is the union operator. It's just like a uppercase U. Everything from 0 to infinity, not including 0. So you can see I use the round parenthesis next to the 0 here and here on purpose, right? And the range? The set of all the outputs, that is to say, the set of all the y coordinates.
0 to negative.
0 to -infinity, that's right. As well as 0 to infinity. So I'm saying this because I can see that in this branch of the graph, the y coordinates are negative. That's what prompts me to write this down. But in this branch of the hyperbola, which is part of the same function, the y coordinates are positive. And that's why I'm going to include this as part of my answer. You need both of those for full credit. Now, if you write down what I'm about to write in your notes, make sure you put real clear next to it that this is incorrect. You will never, ever, ever see that when you're using interval notation. Because when I'm using interval notation is based on the number line, where negative numbers are on the left and positive numbers are on the right. Get the idea? So I'm never going to write this unless I do it by accident, and then you'll correct me. Got it? Because negative infinity means everything to the left of some particular point, right? So what is that? That's 4 of the 9. We got 5 more to go. What's the next one?
Absolute value.
Ooh, that's a fun one. The absolute value function is actually quite simple. It takes whatever the input you give it and just makes it positive, period. If it's positive, the absolute value does nothing. If it's negative, it makes it positive. Make sense? So what's the graph going to look like?
Like a parabola, but with a V.
Yeah, kind of parabola-like. But yeah, but with an important difference, right? If I didn't know any better, I'd just start with 0 and 1 and start picking at several positives, several negatives, and maybe a few fractions, and see if a pattern emerges. But yeah, the absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of negative 1
Is 1.
these 3 points at least are actually completely identical to the parabola. I think the similarity's in there though. The absolute value of 2
It's 2.
and the absolute value of negative 2 makes it positive. The absolute value of 1/2
1/2.
and the absolute value of negative 1/2. After you do what I just did a few hundred more times, you'll start to see some patterns. In fact, actually, if I was to cover this up, you might think it was the identity function. I've erased it now, but you should have it in your notes. You could say it's like the identity function that's been kind of broken at the origin. What would the domain and the range be?
The domain would be all real numbers.
And the range?
Bracket 0 to infinity.
Yeah. What comes next?
Your square root.
What's the square root of 0? Is that a 0? Yeah. Square root of 1?
1.
Seems like everything has 1, 1 on it. square root of 2.
4 and 2.
4 and 2, that's a nice one. Is 2 in the domain?
Yeah.
Yes. Still to the left, right?
Yeah, just because I don't know what the square root of 2 is, doesn't mean it doesn't exist.
It's 2 square root of 2.
Yeah. It's not pretty. It's going to have it's going to be a decimal, right? It's about 1.414, I think. Yeah, so you might need to pull out your calculator for something like this, but the square root of 2 is about right there, I think. How about the square root of negative 1? That's another topic we'll return to in chapter 3. But until we get there, it's undefined. You cannot take the square root of negative 1. Now, if we take the next hour or so and plot 100 more points, the spaces in between these dots are going to start to fill in, but every time you try to plug in a negative number, you're going to come up empty. The shape of the graph will start to look like this. Tell me about the domain and the range. In this case.
Domain would be bracket 0 to infinity.
Why bracket and not parentheses?
Because it's including 0.
Right. So when I'm drawing graphs, and from time to time this will be important on testing situations, sometimes I will put, when the graph comes to an end, like here I put an arrow to indicate that the graph keeps going. It would be a mistake to put an arrow here, right? Because it doesn't keep going. So since it comes to a stop, then the question becomes, well, is the point at the very end part of the graph or not? I'm going to exaggerate a little bit and just put a big filled-in circle. Sometimes I might put a graph with an empty circle. And what does the empty circle mean?
Not including that.
Exactly. All the points close to it are included, but that point in particular is not included. That's what that means. But in this particular case, because the square root of 0 is 0, that means that the end point is actually part of the graph. And so it's appropriate to use a bracket here. How about the range? And what else? Cube root function, is that the next one?
Let's see, 1, 2, 3, 4, 5, 6. Yeah, maybe keywords.
Well, the cube root of 0. And the cube root of 1. Can you think of any more points around the graph? You know, any other
9.
cube roots offhand?
9 and 3.
The square root of 9 is 3.
Yeah.
The cube root of 9 would be 3 if 3 times 3 times 3 was
Oh,
9.
27.
2.
So 3 times 3 times 3 is 27, therefore the cube root of 27 is 3.
Oh,
8 and 2.
2
Or the same can be said for 8 and 2. The cube root of 8 is 2 because,
2 times 2 times 2 is 8.
exactly. Can I take the cube root of a negative number? You can, if you can find a number for which that number multiplied by itself 2 times is that negative number.
like -1.
Yeah. So the cube root of -1 is -1 because -1 times -1 times -1.
-1.
Yeah.
Negative 8 and 2.
Right. Because -2 times -2 times -2 is -8. Do this a few hundred more times, space will start to fill in. You get a picture that looks like this. And therefore, the domain and the range again, especially when you're coming up with the domain and the range based on the graph, these aren't things that you should have to memorize. It's more valuable to be able to just look at the picture and just sort of extract that information from the graph. That's your goal. Let's see here, how many have we done so far?
7.
7, so we've got 2 more. I know there's the inverse square function.
There's,
1 over y equals 1 over x squared.
Yeah, that's one of them.
then, did we do the reciprocal one already?
Yeah.
We did the reciprocal one.
We didn't do the constant function one.
Oh yeah, of course. That one should have been first. I'm calling it the inverse square function. This was kind of important. You know that gravity follows the inverse square law. Inverse square. This is, you would see this if you're in physics studying gravity, for example. But for now, we'll just look at it in an abstract sense, just as an equation. If x equals 1, then y equals. If x equals 2,
1/4.
if x equals 3,
9.
1/9.
1/9.
1/9. So this is, it kind of reminds me of the reciprocal function, but it seems to kind of, it starts to hug the x-axis. I'm not sure how to say this in English. More quickly, sort of. Can you think of a fraction for x that'll work?
What half?
Yeah. If x equals 1/2, what is y?
4.
So you should be thinking like this. First square it, then take the reciprocal. So if you take 1/2 and square it, you get, what's that?
4?
Oh, yeah. So yeah, I'm doing it one step at a time. If you take 1/2 and square it, you get 1/4. But 1 divided by that fraction, 1 divided by 1/4, it's the same thing as 1 times 4 over 1. Division by a quarter is like multiplication by 4. So if x equals 1/2, then y equals 4. did this a few hundred more times, it would start to look like this, but I haven't picked any negative numbers yet. What happens if I pick a negative number? Like, I don't know, -1?
Function, the graph.
Yeah, if x equals -1, then when you square -1, you get +1. And everybody knows that 1 divided by 1 is. So this graph actually, it vaguely looks like the hyperbola that we saw earlier. If you're in the first quadrant, that first section of the graph. But the moment you start plugging in negative numbers, you realize that this graph is actually quite different. Before we had negative numbers for the... So for the same reason, if x equals -2, then y equals
4, -4.
negative or positive. The order is kind of important here too, by the way. So it's a -2 squared is +4, and 1 divided by +4 is a +1/4. Similarly, if x equals -1/2, -1/2 squared, so negative times negative, +1/4. And 1 divided by +1/4 is going to be 4. So it's true. So it's true. It's going to be a reflection. If essentially, it's going to be a reflection over the y-axis. Therefore, the domain and the range?
0, 2, and 3. No?
The domain is the same one as the reciprocal function.
Yeah. So it's going to go from -infinity up to 0, along with everything from 0 to infinity. Positives and negatives are included, just not 0. The range is a little tricky, though. Is the range the same as the hyperbola?
No, because it doesn't go down.
Right. The hyperbola was including the negative numbers as well.
Yeah.
But I don't see any points on this graph that has a y-coordinate, which is negative.
Would it just be parentheses 0 to infinity?
Yeah, the real controversial point is whether I should put a bracket or a parenthesis here, right? Why is it appropriate to use a parenthesis and not a bracket?
Because it's not included in the equation.
Right. I can find lots of points that are with y-coordinates that are really close to 0. But I can't find any points with the y-coordinate that actually is 0. And that's why I'm using a round parenthesis. If I say y equals 3, this would be an example of a constant function. It actually doesn't have to be 3. It really could be anything. But it's a little easier to work with if I have an actual number. I could have said y equals 4 or y equals 5 just as well. This one is slightly baffling since I don't see any x's. If x equals 0, what's y? What's that? Yeah,
Be three.
3. That means this is a point on the graph. If x equals 1, what is y?
3.
If x equals 2, then y equals 3. Strangely enough, this ends up being the hardest of the 9 in many cases to actually graph. Because it's like, oh, I don't get it, there's no x. There are x's, it's just not written in the equation. What if x equals -1?
3.
Would it make a difference if I picked a fraction?
No.
Yeah. So, this one also has a name. It's called the horizontal line. Let me put this back, actually. Domain and range?
Domain, all real numbers, and range would just be 3 in a bracket.
Yeah. Yeah, we don't usually use interval notation for a singleton. This is called a singleton set. It's literally, I don't know if it, hopefully this is clear by now, but there's literally only one number in the range. And that number is 3. So I would just write it like this. That's the curly bracket is used just for a set, right? And that's the usual way we write it. But I guess if I wanted to really force it with interval notation, although I don't think anybody actually does this, I suppose if you wrote this on a test, I would give you full credit. The interval beginning at 3 and ending at 3, including 3, I guess technically that would be right. Yeah.
Would, for the constant function, because I'm looking in the book,
Mm-hmm.
it says the function would look like f of x equals 2. Is that the same as y equals 2?
Yeah. Yeah. Yeah, since we're referring to these as functions, then really I shouldn't be using the letter y at all. These really should be f of x equals. And so if the book says f of x equals 2, you probably saw a graph almost like this one, except just a little lower.
Yes.
Yeah. All right, great.